So let's start. Okay, my name is Timo Schneider. I will present work today that I did during my internship at Intel together with my colleagues James Dynan, Mario Flatschlik and Keith Underwood. Now I am back at ETH and working with our group leader Thorsten Höfler. So in HPC we see a growing trend towards the usage of NVRAM or non-volatile memory. Non-volatile memory has been evaluated in many different contexts and found useful. So we expect to see NVM in next generation machines. What is the reason for this is that NVM is much cheaper than normal DRAM, both in purchase costs but also in power costs. So while we can have maybe hundreds of gigabytes of DRAM in a machine, with NVM, we can actually have multiple terabytes of memory. The downside is that the read latency of NVM is a bit slower than that of DRAM, and the write bandwidth is actually much slower. So for the write bandwidth, we expect only an eighth up to a fourth of the write bandwidth of DRAM. But of course, at a much lower cost, which in turn enables us to have more such memory. The suggested programming model in published papers for NVM is to just map it into the address space and maybe use DRAM as a cache. However, since the writes of to NVM are slow, so for Intel Optane, for example, we get about 5 gigabytes per second write bandwidth. HPC networks will actually outperform this in bandwidth. So what happens if a HPC application sends some big chunk of data to a receiver, and on the sender side this data resides in DRAM, and we have a DRAM bandwidth in that machine of 25 gigabytes per second, and we have a very fast state-of-the-art network which can deliver 20 gigabytes per second. And this network, let's say, is a adaptively routed Dragonfly. This is a fairly standard network topology. And also it is normal to use adaptive routing for Dragonflies. This is the normal way to do it to get high bandwidth. But the receiver actually receives this data not into DRAM, but into NVM. That is not backed by DRAM as a cache. Maybe we ran out of cache space, or we don't even have cache space in that machine. Then the receiver will read this data basically with a speed of 5 gigabytes per second, and all the data will clog the buffers in switches. These buffers are normally there to resolve transient congestion. However, in this case, there is nothing really transient or nothing really congestion about this scenario, but what we really have is just a slow receiver. So what happens if in a network such as this Dragonfly, we have a few of such cases of slow receivers? Of course, we try to minimize this number, but still we expect this to happen sometimes. So here on the x-axis, we plot how many slow receivers we actually have in a communication pattern where each node communicates with one other node in a bidirectional manner, and we just make some of these receivers slow in a BookSim2 simulation in this Dragonfly topology with about 5,000 nodes. And we plot here the percentage of slow receivers. And on the y-axis, we show the normalized throughput. So you would expect this normalized throughput to be 1. However, since we adaptively route this Dragonfly, we use actually more links than absolutely necessary in some cases. That's why even for 0 slow receivers, we only get about 60% of the link speed of this network. And what we can see is that the performance drops dramatically as soon as we have 2 or 3 slow receivers. So of course, the error bars here are very large, because if we only have a few slow receivers and we randomize them over each run, then sometimes it happens that these slow receivers only communicate over a local switch, and then we get almost the top performance averaged over all nodes. So this, of course, is not only plotting the throughput for the slow receivers, but this plots the average for all of them. And we can see that as soon as we have a couple of slow receivers, the performance for all the communication drops very drastically. So we somehow have to address this problem. One way to address this problem is congestion control. So in networks such as InfiniBand, we have congestion control mechanisms. The most popular congestion control mechanism in practice is called Backend, which stands for forward explicit congestion notification, backward explicit congestion notification. And I will demonstrate how this works. So we send some packets to a switch from two different sources. These sources are both fast, so they both send from DRAM in this example, but we have two destinations. One is slow and one is fast. And when the packets in the switch queue up for some reason, at some point there will be a threshold reached of exceeding the buffer space. And when this happens, the switch marks each packet with a second bit with a certain probability. So not every packet will be marked. In this example, we mark two packets randomly. And at some point, they will reach their destinations. And if a second marked packet arrives at a destination, the destination will mark a packet with a backend bit and send this packet or piggyback this backend bit to the sender. And when a packet marked with a backend bit arrives at the sender will slow its injection rate for some amount of time. This usually works well to remove congestion in an InfiniBand network. However, in our example with this slow and fast destinations, what just happened is that this source, which sent only to the fast destination, got throttled for really no good reason. So the only problem in this example was this flow, but actually both flows were impacted by FAC and backend. So we just slowed down this source for no good reason. And we did some simulations on that as well to see if FAC and backend could help us. We ran two different configurations of FAC and backend. One which we call default, which is similar to the default parameters in an InfiniBand network, and one which is more aggressive, so it marks packets at a higher rate and at a lower threshold. And what we can see is if we have imbalance factor of 2, so our network bandwidth is twice that of the memory write bandwidth of the slow receivers, then FAC and backend actually helps. So we can see that if FAC and backend is off, the performance drops much lower than at least with the aggressive FAC and backend in this case. And also with the default FAC and backend, it helps in some range here. But what you can also see is that in the case of zero slow receivers, FAC and backend itself already lowers your performance somewhat because it is not optimal. And if we go a bit higher in the sense of network and memory bandwidth imbalance in slow receivers, then we can actually see that FAC and backend is worse again in performance than not having FAC and backend at all. So we need a different idea. Maybe look elsewhere for techniques how people do congestion control. But the easiest thing to do would be to just throttle sending to a slow receiver, but can a sender really know the receiver's bandwidth beforehand? And no, it really cannot, because this is making a prediction about the future, because we are sending a packet and we want to know what will be the received bandwidth when this packet arrives. And also it's making a prediction about a node that is not us, so we don't even know what other applications are running on that node and so on. So this is fortune telling. We cannot do this in a reasonable way. The problem with FAC and backend was that it ignored flows. It only works on a packet level. That makes it very easy to implement. We don't need much state at the sender and receiver. However, we demonstrated its problems. So an alternative solution is to do something like TCP congestion control. TCP congestion control is actually flow-based. We have a sliding window for each socket pair. The problem with TCP congestion control is that it has actually lots of state, but people have solved this using TCP hardware offload. So you have specialized hardware which manages this space. Due to Moore's law, we have more and more silicon available in NICs, and this is a good way of using it. So the idea is, can we do something similar for HPC networks? Can we implement a receiver-driven, because the receiver obviously has more knowledge about his bandwidth, MPI protocol, MPI, because at the MPI level we actually know about the different flows. And can we use hardware offload to manage all that added state? And for hardware offload, we have a choice between many different architectures and APIs. We chose to target Portals 4 because Portals 4 is quite popular. There are companies which committed to building commercial products. So it's a good target to evaluate. So how does Portals 4 work? We will not give an in-depth explanation here, only enough to understand how our protocol is implemented. So Portals 4 offers puts and gets, but it has two different interfaces. One is the traditional RDMA interface that probably most of you know, but the other interface is a matching interface. So all messages that go through the network targeting this interface include the size of the complete message, the source rank, and the match bits. And at the receiver side, so imagine this is a put going on here, a put request. At the receiver side, we traverse a matching list, and each match list entry also contains match and ignore bits as well as the expected source, and only if the match bits masked by the ignore bits match that of the incoming message, this ME will be a target for this message, and the ME then contains the actual destination address where data should be placed. So in the sense, this is not really put semantics anymore, where the initiator decides where data is placed, but the target can alter where data will go. This is why it's called a matching interface. And we have some additional cool features, which is counting events. So the MEs are able to count certain types of events, such as how many bytes have actually matched this specific ME, or how many put requests or get requests have actually matched this ME. And whenever this happens, a counter can be increased. And we can have triggered operations such as another put or another get, which depend on this counter in the sense of these operations have a threshold, and if this threshold is reached, only then are they executed. This is how we can do offloading in portals. And another feature is this overflow list. So I only talked about we have one list here, and it's actually drawn as one list, but there are two parts to this list, an overflow list and a priority list. And the semantics here is that if we add a new entry to the priority list, Portals itself searches this overflow list, and if something has already matched in the overflow list that would match the new ME that we are planning to append, then it is able to notify us about this scenario. So this is very useful in implementing support for unexpected messages in MPI. So how is our protocol supposed to work at a high level? We are building a receive protocol, obviously, because a rendezvous protocol, obviously, because we don't have a problem with small messages, only with big ones. So in the unexpected case, we will do a send, and we append an ME for gets to the priority list. We only send the first chunk of this message. This message is an unexpected message, so it will match in the overflow list, not in the priority list. And then in the receive, we actually append an ME to the priority list for this message, because it's unexpected, so we don't know that this was already sent. But then Portal searches the overflow list and informs us, hey, I already have a matching message, at least the header of it. From the header, we are able to get the match bits that the sender chose, and we can post a sequence of gets that will actually transfer the data. The word sequence is very important here because we don't want to transfer all the data in one big chunk, but we actually want to use a sequence of small chunks so that each chunk will not fill up all our network buffers, and we only start the next get when the previous chunk has finished, or the previous chunks. Maybe it is useful to parallelize here, as we will see later. And for the wait, we simply have to check a counter on the get ME or a counter on the ME that matches here to see if the transfer is completed. For the expected case, it looks very similar, except for the expected case, we don't need to append anything in this stage, but we already append something at this state. But we have the same idea of transferring the body of the data with a sequence of GET requests. So let's go a bit into details of the implementations. How do we actually implement this protocol? A send is very simple. So for a send, we just do a decision based on the actual message size. If it's a small message, we use the eager protocol, and we simply send the entire message, which is basically only one chunk. But if we have a big message, we go into a rendezvous protocol. We ME append, so we add a match list entry for the gets at the sender side, and we add a counter to this ME to count how many chunks were actually received by the receiver. And then we do a portals put of the entire message. Here we utilize a small trick. Portals hardware implementation, obviously for a big message, will do a rendezvous protocol on a lower level, so it will only send the first MTU, which contains the header data which we need, and actually not send the entire message if it doesn't know that there is a matching ME on the other side. And in this case, the message is already done, but in this state, in this kind of site, we make the request go into a wait get state, because this is what we are actually doing now. We are waiting for these gets to complete at the sender side so that we can tell the application it can reuse the send buffer when it's completed. For the receive, it looks a bit more complicated. So for the receive, we have this receive request, and we append an ME for one chunk into a bounce buffer. And then we wait for a full event. Either it is a link event, so Portals tells us, yeah, okay, with your ME append, everything went fine, and I just appended this ME to the priority list. This means we have an expected message, and we are waiting for something to arrive that matches this ME. But if there is an overflow event, this actually means that this ME matched something that was already in the overflow list. Then we simply copy the first chunk of this message into the user buffer, and we ME append a new overflow ME, because this one we just consumed. We get the size and the match bits from the header, because the receiver has no way of knowing this a priori, because it could have been an MPI receive with, let's say, any tag. And then again, we do a decision based on the message size. If this was a small message, then it means we are done because the message only contained of one chunk. Or if this is a big message where we actually use the rendezvous protocol, then here we post this sequence of gets, and we count how many gets completed in this request counter. And we go into a state wait data. And this sequence of gets is done with triggered operations in such a way that the first C gets, C is like our window size, execute immediately, but all following depend on an increment of request counter. And then we need some way to progress operations, because we don't have full offload now. We show this here, what the test function does. So these are the possible outcomes of the receive and of the send function. And this is actually very simple to implement. So for the send function, all that can happen is that we wait for the get. So if we test for completion, we simply poll this counter. And if we see that the right amount of chunks has been received on the receiver side, we set the request to done. In the receive case, it can be a bit more complicated. So in the case where we are simply waiting for data, we do the same thing. But in the case where we are waiting for the match, we poll the portal's event queue. And the only thing that we can expect here is a put event. So that something has actually arrived that matched the ME. If this happens, we again make a decision on the message size. So if this is an eager message, we copy the first chunk and we are done. But if this is a rendezvous message, we again post this sequence of gets. The problem is that here we don't have full offload, right? So if we would have full offload, everything would happen in the send and receive function, but in this case it really doesn't. So in this case we really need the MPI application to call MPI test on this request to complete it. And the reason why we have this is because we need the match bits in order to post the right match bits for the get. And actually it is impossible to do full offload for the simple reason that when the receive is first, the receive doesn't know anything about the source in case of MPI any source and nothing about the tag in case of MPI any tag. But still, we would need to post triggered gets with the correct match bits here in the full offload case. So it would need to look something like that. But we cannot. In the send, it is similar. So in the send, doesn't know anything about the receive at this point because they didn't communicate yet if the send goes first. And still we need to post the ME for the gets. And we need to send the ready to send message, of course. And only when we get the ready to send message, we actually trigger this get. But Portals doesn't allow us to kind of update something based on this message here. So full offload is tricky. This is of course not a full proof, but I refer you to the paper if you want to see the details of the proof. It's basically a proof done by enumerating all possibilities of what could be the match bits that both sides could choose, and then showing that because MPI allows reordering of send receives, none of these combinations can work. So actually there was an incorrect solution proposed before where they basically suggested using sequence numbers. However, due to this receive reordering that MPI allows, sequence numbers are not valid in this case, because if you use sequence numbers, then you basically enforce that the first send on the sender side has to match the first receive posted on the receiver side. But actually using tags, you can interleave this order somewhat. And there's a more difficult solution, which actually I proposed in one of a previous paper, which requires to analyze the entire communication of an application phase, for example, statically, before the program is actually run. So this is very difficult and not possible in a dynamic setting. So if the communication depends on input data, this is very complicated to do, and we need a special compiler for this. So our approach is simpler. We accept that we cannot have full offload, and now what is left to do is we need to tune this constant C. So how many transfers do we actually want to do in parallel? What we see here is if we make C very small, then we don't have enough parallelism to actually get good bandwidth. But if we make C too large, then we have the same problem that we had initially, that we are just overloading the network. In this benchmark, we use 1% of slow nodes. So this is one of the extreme cases of the first diagram. And we can see, even in this kind of extreme case, we still have a pretty wide range of acceptable values for C. So we just chose something in the middle here, I think 25 for our evaluation. And when we do this, and if we implement this protocol using the software implementation of Portals 4, because unfortunately we don't have hardware available yet, we can see that our protocol matches, or in some cases even outperforms, the standard MPICH protocol for rendezvous. So this is very nice because this basically allows us to deploy this protocol in a cluster even for applications that don't use NVM at all and they have no negative performance impact from this. And if your application uses NVM, then the negative performance impact of slow receivers will be mitigated, as we saw in the previous plot. This concludes my talk, so let's reiterate what we saw today. So we saw that the memory bandwidth network bandwidth ratio is likely to get smaller than 1 for some parts of the address space. This is a very novel problem because previously networking stacks have been designed to simply push data into the network as fast as possible. So we need to rethink this. And we've shown that packet level congestion control is not a good fit for this problem because we need to identify the slow flows and separate them from the fast flows to really solve this problem. So we designed a high-level solution. We did it directly under MPI, and we implemented a receiver-driven rendezvous protocol. And we demonstrate that Portals 4 is actually already powerful enough to offer hardware offload for the RDRP protocol. We prove also that full offload of any receiver-driven rendezvous protocol is impossible using the current Portals. We can discuss later what changes would be required for Portals to support full offload, but this was not a part of this particular work. We also showed that our protocol has no negative performance impact in the absence of slow receivers. So it is ready for deployment in an NVM-equipped machine, even for applications where this problem doesn't arise because they don't even use NVM, there is no negative performance impact. And now I'm ready for your questions. Thank you for your attention.